Hey there, Pre-Calc gang. We're continuing on today in Chapter 6. We're going to do a little combo lesson here, 6.2 and 6.3. They're both a little bit different, but gets us into some more trigonometry and some practical applications of them. So here we go. So first of all, lesson 6.2 is on linear and angular velocity. And velocity, of course, is in a sense like speed. And so we have two different kinds, angular, which we'll always talk about an angle measure. Whoops, I didn't necessarily want to do that. I wanted to get my highlighter out here, sorry. But an angle measure per time unit, like radians per second, degrees per minute, that type of thing. And then linear velocity, this is what we're more used to, a distance measure per time unit, like feet per second, miles per hour, that type of thing. So angular velocity, obviously think angles, and linear velocity, think what you're most used to. So first of all, most of this is kind of common sense. There are a couple little formulas we'll show you, but pretty much common sense. So here's our first example. Determine the angular velocity in radians per second if 6 revolutions are completed in 9 seconds. So if we talk about revolutions, every time we make a revolution around a circle, of course, that's going to be 2 pi radians. So I'm going to do a little unit analysis here. You've probably done this in science quite a bit. I know that there's 2 pi radians in 1 revolution. And so when I multiply these together, I think you see what will happen is that revolutions will actually cancel out. And then I'll get actually what my radians are. So in this case, I'll get 6 times 2 pi, which is actually going to be 12 pi radians, and it says that this is accomplished in 9 seconds, like that. So these are the units I want, so I just really have to divide those two things. And when I take 12 pi divided by 9, I get about 4.2 radians per second. All right? So that's pretty basic, pretty common sense, I think. Just think about how many total degrees or radians in most cases it's this object has traveled, divide it by the time factor that all right. Let's look at this one. A circular serving table in a buffet has a radius of 3 feet. It makes 2.5 revolutions per minute. Determine the angular velocity of a bin of peaches sitting on the serving table, or whatever kind of delectable delight that you'd like. So once again here, I'm going to change colors. So we have 2.5 revolutions in 1 minute is what this table turns around. And I'm just going to start multiplying by stuff to cancel out things. So I have 2 pi radians in 1 revolution, we know that. And finally, since I want to get it in radians per second, I know that in 1 minute there are 60 seconds. So if we look at our unit analysis thing here and see what cancels out, well, the minutes, of course, will cancel out, divide out. The revolutions will cancel out. So what I will have left then is radians per second, and that's what I want. So then I just have to multiply my radians, or my 2.5 times 2 pi on top, and then divide by 60. And what I should end up with then for an answer, you can double check this to see if you get this same answer, 0.26 radians per second. That's how fast that table is moving around. Doesn't seem too fast because you got to be able to grab your food from there. All right, now let's talk a little bit about linear velocity. Linear velocity of a point rotating at an angular velocity of 31 pi radians per second at a distance of 15 centimeters from the center. So the idea here is you'll always have some kind of a circular thing. So again, it's rotating around and around and around. And we could do an angular velocity of this, but we'd kind of like to know how fast it actually is going in a linear type rate. Now, let's go back to last lesson when we learned about this. Remember, this is the formula for arc length, where S is this arc length. Now, anytime I talk about a velocity, there's got to be some kind of a time factor. So let's just divide both sides by t. That's perfectly legal. And then notice that I get s over t equals r times theta over t. Now, anytime we have this, keep in mind s is a distance, and this is a time. So if we have a distance over a time, we can call that a velocity. And notice what we have here. We have r, and then sure enough, isn't this theta over t, isn't that another name for that is the angular velocity, because it is a certain amount of degrees or radians divided by a time factor. So if we know what that angular velocity is, we can simply multiply it by that radius, which is kind of nice. So that means in this particular case, if we want to try to find our velocity, we can simply take our radius, which in this case is going to be 15 centimeters from the center, and simply multiply it by the angular velocity. That's what we're given here. This 31 radians per second is that angular velocity, 31 pi. And so I just multiply those two things out, and I get a decimal. I get 1460.8, decimal point right in there, and that's going to be centimeters per second. So again, there's a nice connection between the angular velocity and the linear velocity, if you can recognize that. But a little common sense will go a long ways on these. All right, here I am driving my bike. Notice that many of you know I have a one-speed blue bike, and my tires are 28 inches in diameter, and so that means that of course the radius would be just 13 inches. But anyway, how fast am I going if my tires are going 150 revolutions per minute? Alright, so this is a bit of a tricky problem, but let's see if we can wade through here and see what we can get. So I know I'm going 150 revolutions in a minute, right? And I know that in every revolution there are 2 pi radians in one revolution, right? And also I know that there are 60 minutes in 1 hour. So if I multiply all that stuff up, I get this monstrous number, 56548.7 radians per hour. Now that's an angular velocity. That's an angular velocity. So I'm going to take that information then and essentially multiply that by my radius. Now notice when it says 26-inch diameter, for my radius I have to use something different. Obviously that's going to be 13 inches. So if I take 13 times, and the tricky part here is I have to get this into miles. How many miles is 13 inches? So notice I do this little unit analysis here just to try to get the units to cancel out correctly. 1 mile is 5,280 feet, in case you hadn't remembered here. And if I multiply all this stuff out, and I have to double check this just to make sure that I got this right, I need to take 13 and I'm going to divide it by 12 times 5,280. You guys can check me out on this, but I get about 0.0002, let's say. So essentially that is my radius in miles. And so now if I multiply my radius times my angular velocity, I should be able to get my miles per hour. So I have 0.0002 times that 56,000, excuse me, 548.7, and you can see that I am zipping along at a huge speed of about 11.3 miles per hour. So these problems are a little tricky certainly, but the key thing is use some common sense and make sure your units All right, we're going on to the next lesson here, and this won't take as long. Graphing sine and cosine functions. A key idea here is that we say that sine and cosine, along with a lot of the other trig functions, are periodic. That means this function repeats itself every certain number of units or every interval. These are all examples of periodic functions here, as you can see the pattern that repeats itself. Now, it is a chart that describes sine and cosine. You probably want to pause this video and make sure you have basically copy all this stuff down. The period is how long it takes to complete one cycle. So you can see for both sine and cosine it takes 2 pi units to complete one cycle. Very similar sine and cosine are the graphs, as you can see here. The domain and range are the same. Just the maximums and minimums are a little bit different here. I think I made a mistake over here on this right column, as you can see. No, I guess it looks alright. This just says where are the maximums and the minimums. So for instance, for cosine, the maximum point here occurs when x equals 0, also at 360 over there, or 0 and 2 pi, and the minimum occurs down here when x equals pi. So take a little bit of time and write down this chart before we move on to the next slide. Alright, here's a typical problem that you might have to do. It says graph y equals the sine of x, pretty standard, but in a different window or a different interval here between 2 pi and 4 pi. So on your graphing calculator, if you have that handy, see if you can follow along here. You're going to simply graph y equals the sine of x, nothing fancier than that in the y equals. But here's where it changes. Your window is going to be different. Notice if I put 2 pi in your window, it will change it to a decimal. 2 pi is about this 6.28 number. And 4 pi, when you put that in, it changes it to a decimal. By the way, for my scale, I often will use pi divided by 2. That's at 1.57. And my y min and max, I go a little bit smaller than -1, a little bit larger than 1, just so you can see it pretty nicely. So here's what the graph looks like. Notice it looks very similar to what it looks like for just a regular trig function, and that's because of the periodic nature of the graph. So the key thing is to set that window correctly, and you should be able to get these. And finally, we'll ask you on these kind of problems to evaluate something like the sine of 11 pi by referring to the graph. Well, if I look at this graph, and even though this is from 2 pi to 4 pi, it could very well be from 0 to 2 pi. So basically this is going to be like 1 pi, 2 pi, and then I'm starting here again. This would be 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi, 10 pi, and sure enough, here's 11 pi. We're back to here again. So by referring to the graph and noticing the periodic or cyclical nature of it, we would be able to recognize that the sine of 11 pi equals 0. And so this will take a while to get used to, looking at the graphs and trying to use the graph to analyze some of these things, but we'll keep working on this in class. So thanks for hanging in there. Kind of a longer video, a combo video today, and we'll see you guys in class. Bye now.